This is a summary of 30 pages of information in something called Booklet by Proton 21 Laboratory in Kiev, Ukraine, well, outside of Kiev. What you see here is the table of contents, and they're talking about their results of doing 200,000 volt, 500,000 amp discharges in a small vacuum chamber. What you see here is their target, which is a 1 centimeter tall copper piece that they aim the discharges at. And you see an example of it on the side, what happened. And then they're talking about measurement of various sorts of information that come from this while they're doing it, which is very important to have this information. But the other thing about it is that they're trying to estimate how much energy came out of that discharge versus what was put in. And that's kind of a tough calculation to make, but they have done that calculation very carefully. And when they do that calculation, they find that they got out, like 400 times as much energy from various sources of radiation than what they put in. They also found that they had a variety of atomic particles coming out of this reaction, which they call hypercompression of the very tip of these things. And so they've got various means of showing you the type of particles they've got, which they've discussed in this thing, and they tell you what the various elements are that they're observing by using the atomic physics. And they also tell you how they're doing it with bubble detectors and other things that are well known in the atomic physics realm. They use a pinhole camera and a fine mesh collimator, which is demonstrated here. And then they've got this sort of X-ray image that they've gotten from this discharge, which isn't coming from it as an X-ray source. In fact, what it looks like is it looks like a stellar X-ray from any star, which is interesting because it correlates with their conclusion that the sun is a super heavy nuclei that's doing antimatter conversion inside of it, and that's where the energy comes from in the sun. A very important point of this work. Now, as we go on here, we can get a discussion of the various methods that they used to analyze the copper that was exposed to this sort of discharge, which compressed the tip by a factor of 8,000 times. Here you see images that shows you scanning electron microscopy X-ray fluorescence. And when you start with essentially pure copper, 99.9957% pure, then they get all of these little areas on these things that have all sorts of other elements, and they do quite a great deal of work on deciding how many atoms of the elements they have. It's considerable. What you see here on the bottom is there's the mounting plate that the copper is on, and there's all sorts of elements that get scattered around there, kind of like a volcanic eruption. And here's more analysis of the type of elements that they have, which it's important to see that they get all the elements of the periodic table from pure copper, not just copper. Then they also track the copper too. And then they use mass spec work to decide, okay, what's the number of protons and neutrons in these various elements that we have. Now, that's a really tricky thing to do, but they have the mass spec equipment, and they did it. And what they kept finding is that the ratios of the various isotopes that you have in these elements are wrong. They're different than the known ratios of isotopes, which is amazing. It means that there has been tremendous amounts of isotopic conversion in these reactions. And so you've got some discussion of the distribution of the various elements and where they're found on the accumulating screens that are at the bottom. And also there's some discussion on actually putting in some isotopes of cobalt and reducing the amount of activity in these things. Now here you've got some more talk about the atomic mass units, and what they're demonstrating is that they have these peaks, like 433 atomic mass units, which are not typically some sort of atomic compound. Now, they get all sorts of unidentifiable X-ray peaks, and the Auger emissions are not totally correct, but when you extend some of the Auger formula into the ranges of non-known masses, what you have is you've got the concept that you have Auger spectra that match theory for super heavy elements, which is incredibly important. So that's the whole story, and it's got to be looked at very closely. This picture shows Stanislav Matamenko, Maxim Koved, and Lev Malowinski, three of the principals at Proton 21. And these guys brought out something and showed it to me that they asked me to describe an object. So what you're going to see here is the object. They asked me to describe the cone seen on the left. That's a centimeter scale. And after I described it as having a smooth surface inside and a rough on the outside, they showed me the object on the right, which is an insulator made out of polystyrene. It has a hole down the center, about an 1/8 inch diameter, that's threaded. And then they said, well, we accidentally left this in the reaction chamber, and we pulled the cone out that you see there after one of our shots. And they said, what do you make of it? And I said, you've just shown us that you can warp space and that interstellar space travel is possible. Startling, stunning.